Now we will introduce the properties of the convolution integral. Here, we only give out the conclusions of 4 properties of the convolution integral. You can learn their proofs from the reference books. Firstly, the convolution integral of f1t and f2t equals the convolution integral of f2t and f1t. In other words, the convolution integrals obeys the commutative law. Secondly, the convolution integral obeys the distributive law of addition. In other words, this expression equals the convolution integral of f1t and f2t plus the convolution integral of f1t and f3t. Thirdly, the convolution integral obeys the associative law. In other words, this expression equals f1t convolutes the convolution integral of f2t and f3t. Fourthly, the convolution integral of any function and delta t equals itself. The 4 conclusions are very important for the following courses. In the circuit analysis, we often use the commutative law of the convolution integral. Next, we use the convolution integral to solve a circuit. You see, this is a current source, resistor, and capacitor parallel circuit. All element parameters are given here. This is a non-zero state circuit. The excitation is a current source decaying with negative exponent from 0 t equals 0. We need to solve the expression of the capacitor's voltage. To solve this circuit, we will take 4 steps. Firstly, we divide the full response into the zero input response and the zero state response. We can solve the zero input response firstly. Secondly, in order to solve the zero state response under this excitation, we should solve the unit impulse response. Thirdly, with the convolution integral of the unit impulse response and the excitation, we can solve the zero state response. Fourthly, by adding the zero state response and the zero input response together, we can get the full response. Firstly, we will solve the zero input response. For the zero input, this is the RC circuit. We use the 3 elements method to solve it. We know the initial value of UC is 3 volts. The infinite value of UC is 0, and tau equals R times C equals 1 second. So UC ZIRT equals 3 times e to the power of minus t, where t is greater than 0. Next, we will solve the unit impulse response ht. We use the observation method introduced in A3. In other words, we need to draw the equivalent circuit from 0 minus to 0 plus. Obviously, IC equals delta t. According to lecture A3, we know UC 0 plus equals 1 over C times the integral of IC from 0 minus to 0 plus equals 1 megavolts. When t is greater than 0 plus, the circuit becomes a first-order RC zero input circuit. Similarly, the infinite value of UC is 0 and tau is 1 second. So we can get that ht equals e to the power of minus t, where t is greater than 0 plus megavolts. Thirdly, we use the convolution integral to solve the zero state response. UC ZSRT equals the integral of e to the power of minus 2 times tau. That is, the excitation is written as e tau times e to the power of minus t minus tau, that is ht minus tau. E to the power of minus t is a constant, so it can be taken outside of the integral. Then it equals e to the power of minus t times the integral of e to the power of minus tau from 0 to t equals e to the power of minus t times e to the power of minus tau from 0 to t. This part equals 1 minus e to the power of minus t. So the expression equals e to the power of minus t minus e to the power of minus 2t volts. Well, t is greater than 0 plus. You should notice that the order of magnitude of ht and et 10 to the power of 6 and 10 to the power of minus 6 are eliminated. Fourthly, we get the full response, which equals ZIR plus the SR. With this part and this part, we can get that it equals 4 times e to the power of minus t minus e to the power of minus 2t when t is greater than 0 plus. Thus, we've completed the whole circuit analysis.